Morning.
Good morning. How are you today?
Doing good.
Awesome. Okay, I just need to hit copy, and here we go. All right, good morning, everybody. Welcome to Thursday, September 24th, 2020, and our continuing journey through the wonders of science and the craziness of our climate change. Really excited to have you all here, and I'm really excited to talk about today's topic, which is a continuation of radiation, a continuation of sunlight, a continuation of what is really a fundamental concept to climate change. And so let's get started. So give me 1 second here. All right, I'm gonna pop the link to our warm-up question in chat. And here's what's going on. So I have these two sheets, a light colored sheet right here and a dark colored sheet right here. In a few minutes, I'm going to take these two sheets outside to the area outside of my apartment, and I'm going to give them a few minutes to soak up some sunshine. Which one of these two, after 5 minutes, do you think is going to be the warmer one? And so go ahead and answer that in the Google form that is linked in chat. For those of you who are just coming in, let me post the link again. Should actually be a perfect day to do this. Maybe a few more people have trickled in, so. Okay. Let me keep track of how many people have responded so far. Make sure that I give you all enough time to do this. Let's see what we have so far. Okay. Couple more minutes. Okay, the poll is quickly filling up. Curious to see what the bulk of the answers are. Mhm. Okay. All right, it looks like we have just about everybody's response in. And let me take a quick look at what the consensus of the class is. And I would say it was pretty one-sided. Let's see here. Here we go. It was very one-sided. It was totally one-sided. 100% of you, 39 of the 39 people who've responded, said that the darker colored sheet will be the warmer one after 5 minutes. And why did you say that? Black absorbs heat while white reflects light. The black sheet will absorb. The white one will reflect. The black sheet would become hotter after 5 minutes because it absorbs sunlight. The white shirt is more reflective. The white shirt is more reflective. The white shirt, the black absorbs more sunlight. Black absorbs more sunlight. Absorbs sunlight better. My assumption is the black color radiates more heat as it happens to absorb. Okay. Ooh, somebody mentioned this thing called albedo. We're going to talk about that today. Dark colors attract more heat. The black cloth will absorb heat while the white one will reflect it. The black sheet will be hotter because it will absorb more heat. The black color is warming quicker because the black will absorb more sunshine. The black is more absorbent. White is more reflective. It absorbs all wavelengths of light and converts them into heat. Sitting in the sun of the fact that the blacker color absorbs more heat than the lighter colors. So it really looks like the general consensus here, and I would say more than the general consensus, is that the black one is going to be the hot one. And the reason why is because it absorbs more sunlight than the white one. So how many of you have ever been told when it's hot outside to wear light-colored clothing? See a few hands going up. Yeah, it's the same principle. It is the exact same principle, this principle of what's called albedo. So what I'm going to do is, in about 10 or 15 minutes, I'm going to go outside and we're going to carry out this experiment. For the sake of transparency, before I even set them out there, I will actually measure their temperatures so that you see that they're the same temperature inside. And then I'll take them out and then we will go from there. So before I do that, though, I do want to tie up a few loose ends from last time and talk about a few very important laws and facts that relate to radiation. So last time, right as we were signing off, we began talking a little bit about this concept of electromagnetic radiation. This is heat that's transferred via electromagnetic waves. Unlike conduction or convection, both of which require some kind of medium, either a solid object, a fluid, a conductor, some kind of other thing, radiation doesn't really need any of that. Radiation can travel through empty space. It can also travel through various objects. That's why you have a Wi-Fi signal in your enclosed home, because the microwave radiation that actually makes up your Wi-Fi signal, bringing my face to your room right now, is able to penetrate walls. So all of that being said, I wrapped up last time by talking a little bit about the wavelength of radiation. So the big differentiating factor of radiation, the thing that differentiates AM radio waves from X-rays, from ultraviolet rays, from visible light, is the radiation's wavelength. And the wavelength is simply the distance between two consecutive peaks. Now, as I mentioned last time, the wavelength of most radiation is too short for us to use our common conventional measurements. They just don't work. So unfortunately, feet don't work, meters don't work, centimeters don't work, millimeters don't even work. Instead, the primary unit that we use is what's called the micrometer, also known as the micron. I mean, we're talking about the size of small bacteria here. And 1 micrometer is the equivalent of 1/1,000,000th of a meter. So if you took a meter, chopped it up into 1,000,000 individual pieces of equal length, each one of them would be a micrometer long. That being said, it is that wavelength that determines everything about the radiation. It also determines how energetic it is. So the frequency and energy of radiation is inversely related, that's just a fancy word for oppositely related, to the wavelength. So what I mean by that is the longer the wavelength, the fewer of those energy peaks you get. So they're both less frequent and less energetic. So a longer wavelength, lower frequency, less energy. And that does kind of make a little bit of sense. So if I had a chalkboard meter long and I drew one giant wave, that wavelength would be a meter, but its frequency would only be 1. On the other hand, if I instead drew 2 waves, now the wavelength is cut in half, but the frequency is double. And each one of those peaks represents more energy. So really the thing I want you to get here is the longer the wavelength, the less frequent and less energetic the wave is. And the opposite's true too. If we shorten up that wavelength, we're going to have a more frequent, more energetic beam of radiation. So a long wavelength, low frequency, low energy. Short wavelength, high frequency, more energetic. And all kinds of radiation, every type of radiation is governed by this fact. So all types of radiation are governed by this fact. So right now, in the room you're sitting in, there are AM radio waves harmlessly passing through your body, because AM radio waves are really long. That being said, if you've ever listened to an AM radio station, you know the reception kind of sucks. That's because it's so low energy. It is so low energy that the reception sucks. FM radio waves are a little bit shorter. They're a little bit more energetic. You get better reception. TV, even a little bit shorter. You get better reception. But on the other end of all of this, ultraviolet waves, X-rays, gamma rays, those are what are called ionizing. Those are so energetic, they can actually knock electrons off of the molecules inside your body, which can trigger mutations, breakdowns that can actually cause your organs to shut down. All kinds of crazy things can happen. So, two very different ends of the spectrum. Waves that harmlessly pass through your body versus waves that can kill you. All of this is summed up in what is called the electromagnetic spectrum. And so you don't need to memorize this or anything like it. But what I do want you to know is simply the longer the wave, the less energetic it is. So those AM radio waves, which are at the top of the EM spectrum, very, very long, very, very weak. Now, one type of electromagnetic radiation that I really do want to give a little bit of service to, visible light. So how many of you have ever heard of Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. Your teachers taught you that probably in grade school or in middle school. Well, I have some bad news for you. Your teachers lied to you. They taught it to you in reverse. In order of wavelength, it's actually violet, then blue, then green, then yellow, then orange, then red. Violet is the shortest wave. Red is the longest wave. Now, before you go off and say, wow, you badmouthed my 5th grade teacher, they teach it that way because it's the order of the rainbow from outside to in. So they're not doing anything wrong. I'm just saying that in terms of actual wavelength, they reverse the order. Pretty cool concept, actually. But that being said, each color that you see right now inside your room is a different wavelength of radiation that your eyes are sensitive to. And then your eyes then trigger a response to your brain and it registers as a color. All right, now that being said, I would like to ask a poll. So, which of these two colors should be most energetic? Red or blue? If you don't see the poll up on your screen, you can just type your answer in chat. So, which one is more energetic? Red or blue? Now remember, the longer the wavelength, the least energetic. The longer the wavelength, the least energetic. Energy and frequency are oppositely related. And as I mentioned, violet is the shortest wavelength, red is the longest. What I loved was that as soon as I said that, I got the proportion of people who were voting for one of them changed dramatically. And I'm sure some of you are thinking, man, I wish I could change my vote right now. I don't know if you can on here, but it's totally fine if not. So there's no points attached to this. So let's see here. I've got almost everybody. I've got 6 people who still haven't. Again, if you can't see the poll, you can type your answer in chat over here in the chat box. I tried giving a poll yesterday in my Deanza Met 12 class, and like 10 people couldn't see the poll. So it does have to do with the type of or the version of Zoom you have on your computer. If you have an older version, you might not see it. All right, let's take another 15, 20 seconds. Got almost everybody, but a few people haven't voted yet. So once again, which color of visible light should be the most energetic? right. I'm going to end the poll and I'm going to share the results now. What's funny is actually the way that the lines are actually colored is the exact opposite of the answers. So 20 of you said blue, 17 of you said red. Now you didn't actually see how the votes progressed, but when I first asked the question, it was overwhelmingly red. And then as soon as I said, remember, the shorter the wavelength, the more the energy, the votes very quickly changed from red to blue. The correct answer is blue. Blue is the more energetic of the two. The reason why is because it's the shorter of the two wavelengths. Red has a little bit longer of a wavelength. Blue has a little bit of a shorter wavelength. So don't sweat if you didn't get that, but I just wanted to see what people's thoughts were. So once again, red is least energetic. Violet would be most energetic because it's the shortest wavelength. And so your choices were red or blue. Here, blue was the shorter of the two, so it had the most energy. All right. So now let's actually talk about what emits radiation. So I've talked about radiation, I've talked about visible light, I've talked about AM waves, FM waves, and so on. But actually, it's really important to know what emits radiation and what dictates the type of radiation it emits. Right now, if you're sitting in a room that has a light on, I've got two lights on so that I don't look dark on here, so it's easier to see me. But if you're sitting in a room with a light, that light is emitting a type of radiation. It's emitting visible light. What allows it to emit that visible light, though? Well, it all comes down to temperature. And this can be summed up in these three key radiation laws. The first law, I affectionately call it Oprah's law. It's actually not a law, it's a fact, meaning it is true. The other two laws are called Wein's law, named after a German physicist named Wein, and the Stefan Boltzmann law, named after two physicists named Stefan and Boltzmann. So let's talk about these three laws. So, Oprah's law. What emits radiation? Well, as I suggested at the end of class last time, the fact of the matter is every object that has a temperature above absolute zero emits radiation. That includes everything you see around you right now. So think about it. The shirt you are wearing is emitting radiation. The computer you are sitting at is emitting radiation. The chair you are sitting on or the bed you are sitting on is emitting radiation. The walls around you are emitting radiation, and 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 you are emitting radiation. Everybody is emitting radiation. That's why I call it Oprah's law. It's not really a law, it's just the way that I have people remember it. Just the idea is anything with a temperature above absolute zero emits radiation. So right now, everything around you is emitting radiation. All right, now that being said, what kind of radiation do you think is being emitted by everything around you? Take a guess. What kind of radiation do you think is being emitted by the objects around you right now? Well, why don't I ask you, what kind of radiation do you think you emit? Somebody private messaged me phone radiation. That's actually a type of microwave radiation. What else? What kind of radiation do you think the objects around you right now are emitting? What kind of radiation do you think you emit? Somebody private messaged me infrared radiation. All right, so I've got a vote for phone radiation, that's microwave radiation. I've got one for infrared radiation. Let me ask you this, do you think you emit visible light? I see some head shaking. Well, let me prove to you that you don't emit visible light. Let me turn off this light here. Let me turn off this light here. I look a lot darker now. Why? Because I turned off the things that do emit visible light. You actually don't emit visible light. You don't emit visible light. So think of it this way. You are all radiant, but unfortunately, none of you are glowing. You are all radiant, but unfortunately, none of you are glowing. But why aren't you glowing? Well, to answer that question, we have to look at Wein's law. That's the second law. Wein's law states that the warmer the object, the shorter the wavelength. And this is actually summed up in this little equation right here. Now, don't worry, I'm not going to make you remember this or memorize this or anything like that. What I would probably do is give you a temperature in Kelvin and you would just plug it in. But this law states that the radiation most commonly emitted by an object, so the radiation most emitted by an object, is equal to 2,897 divided by the object's temperature in Kelvin. And whatever you get on the other end is the average wavelength of the radiation most emitted by that object. Most of the radiation an object gives off is at or around that lambda max. Lambda means wavelength, max means just most emitted. What I really want you to get though, the main point I want you to get here, the warmer an object gets, the shorter the wavelengths it emits. Now, let's actually figure out what is our wavelength. So average human temperature, 98.6 degrees, converts to 310 Kelvin. So the average human temperature is 310 Kelvin. So our wavelength would be 2,897 divided by 310. That gives humans an average, that gives humans an average wavelength. So human temperature equals 310 Kelvin. Average wavelength of a human would equal 2,897 divided by 310. That gives us a wavelength of 9.35 micrometers. So humans, us, we emit radiation approximately at 9.35 micrometers. And that is actually infrared radiation. That is actually infrared radiation. So the person who messaged me and said we emit infrared radiation, you are correct. You are correct. Now the average wavelength of visible light is actually between, my cursor disappeared again. I hate it when Where did it go? Okay, here we go. So the average wavelength of sunlight, the average wavelength of visible light is approximately 0.4 to 0.7 micrometers. Oh gosh, that's drawn very poorly. So in other words, in order for us to emit visible light, we would have to get much, much warmer. That is the other part of the bad news I have. So yes, you are all radiant. But unfortunately, you don't glow. And why don't you glow? Because you're not hot enough. I know my professor just took a really big hit right there, but you are not hot enough to glow. Instead, we emit infrared radiation. If we wanted to emit visible light, we would have to become way, way, way hotter, like above burning temperature. So you'd have to be burning hot to be glowing. Sorry to break the news to you. So you can't say you're glowing on your dating profile. Bad news, I know. I'm the bearer of bad news. But I promise you it's okay. Let me now get rid of that. Sorry, give me 1 second here. There we go. However, if you've ever noticed before that a coil of metal will get really, really hot and then start to glow, like if you have a hot plate at home or a with like a coil that heats up, that's the kind of oven I have. Once it heats up, it starts to glow. Well, the reason why that happens is because the hotter the object it gets, the closer and closer and closer to visible light the object emits. This is also why liquid hot magma glows, because the temperatures of liquid hot magma become so high that they eventually enter the visible light spectrum. And so they begin to glow. So that's why that actually even happens. So that's why hot things glow, because we heat them up and the wavelength they emit gets shorter and shorter and shorter. Boom, visible light. That's what's happening there. One last law that I need to bore you with. The last law that I need to bore you with is called the Stefan Boltzmann law. So the previous law, Wein's law, tells you what kind of radiation an object emits. The Stefan Boltzmann law tells you how much of it emits. And again, because we're science-y, we've got these crazy equations. Don't worry, I'm not going to make you write down this equation or do anything with it. I just want to show it to you. But the main result of it is, the warmer an object is, the more radiation it emits. The warmer an object is, the more radiation it emits. So think about the objects inside your room right now. The coolest objects aren't emitting a lot of radiation, whereas the warmer objects are emitting a lot more radiation. So the warmer the object is, the more radiation it emits. I'm going to do another poll now. Here is the other poll. I'm going to give you two objects, and I'm going to ask you, first, which one emits more radiation, and second, which one emits longer wavelength radiation. So just to review, the warmer the object, the shorter the wavelength. The warmer the object, the more radiation it emits. So Which of these objects emit more radiation, and then which of these objects emit longer wavelengths? The Earth or the sun? Here we go. So which object emits more radiation? Which object emits longer wavelengths? So remember, the warmer the object, the more radiation it emits. The warmer the object, the shorter the wavelength it emits. And once again, if you can't see the poll, you can answer in chat. So I'm asking for Earth versus sun. Which one emits more radiation? Which one emits longer wavelengths? Got pretty good voter turnout so far. Hopefully we see this kind of voter turnout in the next election, not to get political. All right, let's wrap it up in 15 seconds. Last call for votes. And let's see what people said. So it was a landslide on both questions. The first question, which object emits more radiation? Those of you who selected the sun are correct. Now, it has nothing to do with the sun's size. If we had a chunk of sun and a chunk of Earth that were the same size, the sun would still emit more radiation because it's hotter. On the other hand, which one emits longer wavelengths? Well, the warmer the object is, the shorter the wavelength. So the opposite is true too. The cooler the object, the longer the wavelength. The Earth emits longer wavelengths of radiation. So overwhelmingly, you got these right. Now this becomes super fundamental to the science of climate change. This becomes super fundamental because this is actually how the greenhouse effect works, which we're going to talk about next week. Here we go. So, first off, both objects have a temperature above absolute zero. So according to Oprah, not really, but they both emit radiation. The sun is really, really hot. At its surface, it has a temperature of 6,000 Kelvin. So the sun is really, really hot. The Earth, on the other hand, is not nearly as hot. The sun emits a lot of radiation, and it mostly emits it in ultraviolet, visible light, that's why the sun glows, and near infrared. For the remainder of this term, for the remainder of this course, I'm going to keep using this next phrase to describe sunlight. We call this shortwave radiation. So the sun emits shortwave radiation. On the other hand, the Earth, with a much, much cooler temperature at the surface, emits mostly infrared radiation. We call this long-wave radiation. So the sun emits shortwave radiation, the Earth emits long-wave radiation. I shall say that again. The sun emits shortwave radiation, the Earth emits long-wave radiation. There are very few things that I would want you to take out of this more than that. The sun emits shortwave radiation, the Earth emits long-wave radiation. That will be fundamental when talking about the greenhouse effect. One last time, the sun emits shortwave radiation, the earth emits longwave radiation. Shortwave radiation from the sun, this solar radiation, is mostly a cocktail of visible light, that's the radiation that the sun emits, which is why it glows, a decent chunk of near-infrared radiation, and a little bit of ultraviolet radiation. This is the stuff that gives us burns over here. But the bulk of the sun's radiation that it emits is visible light. The Earth, on the other hand, because it's colder, it emits much less radiation, and it emits it in much longer wavelengths. The average wavelength of the Earth, the average wavelength that the Earth emits is right around 10 micrometers. That's well in the infrared spectrum. And because it's colder, it also emits a lot less radiation. Hence, its little peak is not nearly as tall as the sun's. This is just a little diagram that looks like it was drawn by a kindergartner, but it was actually drawn by a grad student aged Terrence. And what it was is the sun, nice and hot, gives the Earth shortwave radiation. That's what the sun heats us up with. That shortwave radiation then reaches the surface of the Earth. The Earth and its atmosphere absorbs a good chunk of this, heating itself up. Now, as the Earth heats up, it emits more long-wave radiation. So it gets shortwave radiation from the sun, it emits long-wave radiation from the Earth. So it gets shortwave radiation from the sun, it emits long-wave radiation from the Earth. If you've ever noticed before, like on one of those really smoky days like we had a few weeks ago, the apocalypse sky day as I called it, when something actually shrouds out the sun, it begins to feel a little bit cooler. And the reason why is because it's that sunlight that heats the Earth up. Well, about 3 years ago, we had a big eclipse. It was a big deal in the United States. We're going to have another one in about 4 years. And it actually had an impact on the temperature of the region that it was a total eclipse in. So right up here, this graph, this was taken from Salem, Oregon, which was like right in the middle of the path of totality. The sun came up at around 6:30. As the sun got higher in the sky, the intensity of incoming sunlight became greater and greater and greater until the eclipse started. As soon as the eclipse started, the amount of incoming sunlight dipped until totality hit, and once totality hit, there was no incoming sunlight. Well, during that same time, temperatures, which are usually going up in the morning, as the sun gets higher in the sky, temperatures usually go up. Well, here, temperatures actually took a little dip. They went back down. And then as soon as the eclipse, the moon passed over the sun and the sun came back out, temperatures very quickly recovered and then reached their high later in the day like they normally would. So obviously sunlight is essential to Earth getting its heat. I mean, that's pretty obvious. And this delicate balance between incoming sunlight and outgoing long-wave radiation is really what governs Earth's temperature. So let's talk a little bit about how that works. So, what does the Earth do with the radiation that hits it? So, once that radiation makes that 93 million mile journey from the sun all the way to the Earth, we usually consider it to have reached the Earth once it hits the top of Earth's atmosphere. Once that happens, once it's entered the Earth system, the Earth does two main things to it. It either absorbs it or it reflects it. So the Earth either absorbs the radiation that hits it or it reflects the radiation that hits it. Well, of the radiation that's absorbed, 19% is absorbed by the atmosphere and clouds. So of all the radiation that reaches the Earth, 19% of it is absorbed by gases in the atmosphere and by clouds. Another 51% is absorbed by the ground. Put together, these two, absorption by the atmosphere and absorption by the ground, account for 70% of all of the radiation that reaches the Earth. So the Earth absorbs 70% of all of the radiation that reaches it. The Earth absorbs 70% of all of the radiation that emits it. What happens to the other 30%? Well, the other 30% is either reflected by clouds, that's 20% reflected by clouds, 4% reflected by the ground and the ocean, and the remaining 6% is scattered. And it's the scattering that actually produces colors. So if you've ever wondered, why is the sky blue? Scattering. The gases in the atmosphere scatter blue light way better than the other wavelengths. So it gives us a brilliant blue color. On the other hand, at night or at sunset, the sky usually looks yellowish to reddish. Well, the reason why is because as the sun is setting, it's actually traveling through, sunlight is traveling through more atmosphere, and that actually causes a lot of the blue light to scatter away. And the remaining light is red light. So you get that nice red sunset. And so grand total, these three things, oops, sorry, I'll go back. These three things, reflection and scattering, make up 30%. So they make up 30%. So 70% is absorbed by the Earth, 30% is reflected by the Earth. What's crucial here is that if we were to change this balance, if we were to change this makeup, maybe less reflection, more absorption, the Earth would become hotter. On the other hand, if we were to instead make the Earth more reflective, meaning that the Earth would reflect more radiation and absorb less, the Earth would become cooler. So this delicate balance between reflection and absorption is really, really crucial for maintaining our wonderful way of life here on Earth. Really quickly before I move on, let me clear those drawings. And, oops. So this little graphic here is just a visual of the previous slide. If 100 units of solar radiation come in, 51 of them are absorbed by the surface, 19 of them are absorbed by the atmosphere. The remaining 30 are reflected, 4 by the surface, 20 by clouds. This is why clouds have that beautiful, brilliant white color to them. And 6 by the atmosphere. And that's what gives us our colors. So what I'm going to do is take a few moments and talk about absorption. And then I'm going to go outside and do this little demonstration. All right. So let's talk about absorption real quick. Many objects are very, very good at absorbing almost all of the radiation that hits them. These are what are theoretically called black bodies. And they're called that because they absorb almost all of the radiation that hits them. In fact, those laws I told you earlier, Wein's law and the Stefan Boltzmann law, those are approximations for black bodies. That being said, we're not going to go any deeper into that concept. Just some objects absorb almost all of the radiation that hits them. Earth's surface is an excellent example of this. Most of the radiation that hits Earth's surface gets absorbed by the Earth. A black colored t-shirt is another. It absorbs most of the radiation that hits it. On the other hand, there are some objects that some wavelengths of radiation are completely transparent to, while absorbing other wavelengths. So how many of you have ever heard of a selective listener? How many of you have ever heard of a selective listener? Can somebody tell me what is a selective listener?
Someone who picks and chooses what they want to listen to.
Bingo. Someone who picks and chooses what they listen to. So they listen to some things, but not to others. So they listen to some things, but not to others. Well, I always tell people that's like me when I look at my professors. I read the good reviews. Everybody's stoked on me. And then I ignore the bad ones. Okay, well, I'm going to ignore that. Most of my family. Nice. Nice. I'm guilty of it sometimes too. That being said, a selective absorber is a gas in the atmosphere that only absorbs certain wavelengths of radiation. Otherwise, they either reflect or are completely transparent to the other types of radiation. Now, how does this relate to our class? How does this relate to climate change? Well, we'll talk more about greenhouse gases next time, but all of the different greenhouse gases, carbon dioxide, water vapor, ozone, nitrous oxide, and methane, they are all selective absorbers. They are perfectly transparent to most shortwave radiation, meaning they let sunlight just come on in. But many of them absorb at least some of what the Earth gives off. They absorb at least some of what the Earth gives off. So that's how that happens. So that's exactly how that happens. So now let me talk about the main thing I want to talk about right now with this little activity, scattering and reflection. So one word that you may hear in the future is what's called transmission. Transmission is simply when radiation passes through a material. It's transparency. Basically, radiation just passes straight through. But many objects at least reflect some radiation. Reflection happens when a certain wavelength is not absorbed and it's not transmitted, meaning it doesn't just pass right through, but instead the radiation bounces off the object. The amount of incoming shortwave radiation reflected off of an object is what we refer to as the object's albedo. So those of you in the warm-up question who mentioned albedo, you were ahead of the game. The albedo of an object is the amount of radiation that is reflected off of it. So when I talked about the Earth a few moments ago, I said that the Earth reflects 30% of the radiation that it reflects 30% of the radiation that hits it. Therefore, Earth's albedo is 30%. Earth's albedo is 30%. All right. Let's do this activity real quick. So what I'm actually going to do right now is I'm going to sign on from my cell phone. I'm going to sign on from my cell phone to Zoom. Let me do that real quick. I always have to remember where I put my Zoom app. There it is. And just to make sure that I am not tricking anybody, what I will actually do before I do this, let me sign in. Oops. Okay, give me 1 second here. Here we go. And, okay, let me go to my meetings. Let me sign in. Here, I'm going to mute myself on this microphone because otherwise you're going to get a wicked echo. Oh, there we go. So can people hear? Oh, I still got that wicked. Oh, I know what to do. Okay, so can people hear me right now? Loud and clear, all good?
Yeah.
All righty. Awesome. So, is there a GC for this class? I don't know what a GC is. What is a GC? Group chat. Oh. I don't know, actually. I mean, you should be able to chat using this chat box, but I actually don't know. Okay, so here I am in my dirty office. Let me really quickly flip this around. So here we go. I have the two sheets right here. So this first one is a dark sheet. This is the dark sheet. Using this little thermal infrared thermometer. This is actually a thermometer that I can use to measure the temperature of an object based on the radiation it gives off. Let's actually see what the temperature of the dark one is. Right around 76. Okay, I have no friends here. I'm sorry. I can be your friend. So 76. And then the temperature of the lighter colored one. Let's see here. $74, so slightly cooler. But they're almost about the same temperature. They're almost about the same temperature. Well, what I'm going to do right now is I'm going to go outside with these. I'm going to go outside with these real quick. Don't mind how messy my office is. I'm going to go outside really quickly and set these down and show you the impact that the color of the shirt that you wear can greatly influence the temperature. Oh, it's a nice, bright, sunny day out. Here we go. We're outside my apartment now. Nice, bright, sunny day. Let me lay down the dark cloth and the light cloth. And let's give it just a couple of minutes to soak in that sunlight. Just a couple of minutes to soak in that sunlight. Are you all able to see the white cloth and the dark cloth?
Yes.
Yeah.
Awesome. Okay. So let's just give it just a couple of minutes. Just so that you know I'm not doing anything to them. So right now what's happening is the lighter colored cloth, the white cloth, is reflecting a lot of the sunlight that's hitting it. However, the black cloth doesn't have that luxury because it's so much darker. Well, it is so much darker because it absorbs most of the radiation that hits it, most of the sunlight that hits it. The temperature difference between these two in just a few minutes is going to be insane. So let's just give it a moment to do that. This should be the last beautiful day before it gets really hot. It's already feeling pretty hot today. Hopefully I'm not annoying my neighbors. Normally I would just take everybody outside and do this. The wonderful days of the pandemic. Not so wonderful. Okay. All right, let's take a look here and see what we got so far. So the temperature of the dark one . The temperature of the dark one, 96.3 Fahrenheit. Now let's look at the temperature of the light colored one. The temperature of the light colored one, 80.5. So I just had these out here for just a couple of moments, really. Not even that long, not even the 5 minutes I said I was gonna have them out here for. And just in that short period of time, it was already a very, very noticeable difference. A very noticeable difference, a 15-degree difference, just in a few seconds out here. Now, how does this relate to climate change? Well, Earth's polar ice caps act very much like the white-colored sheet. They reflect a lot of the sunlight that hits them. On the other hand, the land beneath those ice caps, or the ocean beneath those ice caps, behave a lot more like the dark-colored sheet. They behave a lot more like the dark-colored sheet. Now, what does that actually mean? What that means is that as ice caps melt, what essentially Earth is taking off its white t-shirt and it's putting on a dark t-shirt. That's going to make the Earth much, much hotter. This actually triggers what's called a positive feedback loop. All right, so let me grab these and I'll go back into the office and finish up today's lesson. Give me 1 second. Okay. I'm still here, I just muted my video. Yeah, even holding these two, the light colored one definitely feels a lot cooler than the dark colored one. Okay. Heading back into my office now. And now one thing I will say, all right, let me sign out of here real quick. And all right, can everybody hear me again?
Yeah.
All righty. Oh wait, Professor T, WYA, where am I at? Is that what that was meant to say? I'm terrible with abbreviations, by the way. Half the time I say WTF, so hopefully that made somebody laugh. So I'm back. Can you all hear? Loud and clear? All good?
Yeah,
All good? Check, check.
we can hear you.
Andrew, do you have a question? Let me make sure. Oh, you know what? I think I need to. Okay. Oh, okay. All good. All right. So let's get back to this. So the albedo of an object greatly determines what it does with incoming sunlight. And the reason why this is such a scary thing is that as our ice caps melt, our ice caps are very, very reflective of sunlight. They help keep the earth cool. But as the earth begins to warm, those ice caps will melt. And as they begin to melt, we might have some pretty big problems. So it is actually something pretty alarming, because what's left behind is darker colored surfaces, and those darker colored surfaces are going to absorb more radiation, heating the earth up even more. So in this case, warming basically kicks off a feedback that leads to more warming. And everybody's on here putting together a Discord server or a group chat. I love it. I love it. I hope it's helpful. I really hope it's helpful. I think that that's a great idea. Okay, so when talking about albedo, whoops, 1 second. Once again, the albedo of an object is the fraction of light reflected by the object. White objects, like that white sheet, have high albedos. Black and dark colored objects have low albedos. So I have 3 circles here, and the lighter the color, the higher the albedo. The lighter the color, the higher the albedo. Now, I'm actually going to mention albedo a few more times in this course. Next week, I'm going to talk about the greenhouse effect between Earth and Venus. And this is going to be a big thing that's covered. So this table right here just shows the average albedo of different objects. You don't have to memorize this. You don't have to do anything with it other than it's just good to kind of know some of the average albedos of things. Fresh snow can have an albedo as high as 95%. Ice has an albedo between 30 to 40%. The fresh snow on top of the ice oftentimes has an albedo much higher. Clouds can have albedos anywhere between 30 to 90%, depending on how thick they are. Earth's average albedo is 30. Mars, our next door neighbor, has an albedo of 17. Venus, our other next door neighbor, has an albedo of 78. What that means is that Venus actually, believe it or not, even though they're closer to the sun, they receive much less sunlight than we do because their albedo is so high. Ironically, Venus is also the warmest planet in the solar system. We'll talk about why next week. So obviously these nice snowy fields, very high albedo. These dark forest canopies, very low albedo. And then just a few words about scattering. So scattering occurs when sunlight hits a gas in the atmosphere, and the gas just scatters the light in all different directions. What this does is this causes the light to be less intense once it reaches the surface of the earth. And it's also what gives us those beautiful blue colors that we see in our sky. Our sky is blue because the particles of atmospheric gas actually scatter most light, or scatter blue light, much better than other types of light. The remaining light that reaches us, or the remaining light that heats us up, isn't blue light. It's other wavelengths. However, later in the evening when the sun is low on the horizon, the sunlight has to pass through at 12 times as much atmosphere as it did when it was high in the sky. as a result, all of that blue light is scattered away, and you get that beautiful red sunset color. That's all I'll mention about scattering or optics or anything like that. So the last thing I'll mention today before I wrap class up is, I'll go back for a second in case you need to finish jotting down anyway. Trust me, I'm looking for the same thing, Shayna. I don't know if I pronounced your name correctly. I'm so sorry if I didn't. I'm looking for the same thing to go and grade papers and write up lessons.
Yeah, I usually like go to the library or like a cafe to do homework so that I can like stay more motivated. But if I'm just at home, I can't stay motivated as well. So kind of struggling.
Ever since this pandemic started, I feel like it's not the same being home. Like, you're not as productive. At least I'm not as productive.
Me neither.
I totally understand where you're coming from there. I miss my office.
Yeah.
Okay, last thing I'll mention before I wrap up today. All of the stuff I talked about, incoming radiation, outgoing, scattering, reflecting, and everything, is actually all balanced. So rather than thinking about all those different components, let's just think of two. What comes in and what goes out. Think of your bank account. What would happen to your bank account's balance, the amount of money in your bank account, if your income is greater than your spending? Your income is greater than your spending. What would happen?
It would continue to get bigger.
Yeah. Your account balance would go up, 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 and up. So what would happen to Earth's temperature if incoming sunlight was greater than outgoing radiation? What would happen to Earth's temperature?
Would it get hotter?
It would get hotter. We will eventually die from the heat as well. Somebody private messaged me that. Okay, what would happen on the other hand? Let's say you had a bad month. You didn't make as much, and yet you still had a lot of expenses. And so your income was less than your spending. What would happen to your bank account balance in that case?
It would go down.
It'd go down. Yeah. You would be spending down your bank account. Now, I'm not an accountant or anything like that. I overdrafted a lot when I was in college, long story. But that being said, when income is less than outgoing, Earth would cool. So when income is greater than outgoing, Earth warms. When income is less than outgoing, Earth cools. Now, how does this relate to greenhouse gases and climate change? Well, as the Earth is heating up, or the Earth is heating up, because those gases are decreasing the amount of radiation leaving. The amount coming in stays the same because they're transparent to it, but the amount going out decreases. That makes the Earth warmer. So that's what's happening. I'll talk more about energy balance next time. I do want to make a couple of announcements. We were supposed to have a quiz scheduled for today. I'll get to that in a second. I'm actually going to talk about the homework in a second. We were supposed to have a quiz today, but in the mad dash that I've been going through this last week, I never posted the study guide. So I posted it now. We're going to do that quiz next week. It's going to be the same structure as the last quiz, meaning I'll release class a little bit early, and then you'll have until the end of the weekend to do it. So that study guide is up now. The other thing is the homework. So homework number 2 is up on Canvas, and the deadline is actually today. That being said, because I'm just now mentioning that, or because I'm giving that reminder now, I will waive the late penalty on it. So if you turn it in late, I'll still accept it full credit. Okay. Somebody just asked, I'm wondering if for the first question, do we analyze the most recent maximum and minimum or each individual one? So I actually want you to analyze each individual one. So there should be 4 or 5 maximums. I want you to list all of them. And then the same for the minimums. I want you to list all of them. How late is late? Is Tuesday okay? I'll just extend it to Tuesday. I'm fine with that. I'll go ahead and do that. I'll extend it to Tuesday. All right. So that's it for today. If you have any questions, comments, concerns, and or threats, I can hang out for a few minutes. Otherwise, it's going to be a hot one this weekend. Try to stay cool. I hope you all have a great weekend, though, and I'll see you all next Tuesday. So long.
Thank you.
Thank you.
Thank you.
Bye.
You have a nice day.
You too.
Thank you. Have a nice one.
Thank
Bye.
you.
Professor,
Hi, how can I help?
I had a question about number 1. I know we just kind of talked about it briefly, but
That's okay.
trying to look at it right now, and when it came to the temperature, I don't know why I'm confusing myself so much, but it's like when I see the negatives, especially with Celsius, I always get confused. So how do we really identify the maximum and minimums? Like, what would that
So
be? Temperature.
So the positives represent warmer than current time. The negatives represent colder than current time. And so when I'm looking for maximums, I'm just looking for those peaks, those really pointy peaks.
Okay.
And then the minimums are kind of like that lowest point on the dip.
Okay.
I don't know if that makes sense.
Yeah, no, that's what I thought, but when it came to, like, you know how with negatives, the closest to 0 is, it's just that whole entire rule of, like, negatives that I was, like, confusing myself with.
That's okay.
Cool.
Hope that helps.
Yeah, it does.
Awesome.
I think. And then also, yeah, for C, we just look at that time period between 100,000 and 50,000 only.
Mhm.
Okay, just clarifying. Thank you.
Absolutely. Got a few more people in the room. Are there any other questions I can help out with right now? All right. Thank you so much, everybody. Those of you who can still hear me. If you do have any questions, don't hesitate to drop me an email, or you can just say, wait, real quick before I sign off right now. Otherwise, I will see you all on Tuesday.